Welcome engineers to 1.3.3, which Introduction to Thermodynamics Part 2. In Part 1 we talked about what thermodynamics is, the difference between thermal energy and temperature, the different temperature scales that we deal with, the three different ways that heat can move from point A to point B, and then we talked about the three different laws. The first law of thermodynamics, how energy can neither be created nor destroyed. The second law, that energy flows from hot things to cold things. And then we did an example of heat transferring from point A to point B through conduction using specific heat, where we took a hot piece of aluminum and we put it in cold water and we calculated how much energy is transferred from the block into the water, and it was 21 kilojoules. Today we're going to do some more examples. How does heat go from point A to point B using radiation and other conduction methods? So here's some other equations that we're going to use. P, power. Power is equal to energy divided by time. That's what this stands for, power. The rate of energy transfer. Power. Q, energy. And then T stands for time. So power is equal to energy divided by time. So watts is equal to joules per second. That's what this means here. So P that would be watts, and that's a joule per second. P again, power. And you have this K, thermal conductivity. How well a material conducts electricity, or conducts thermal energy. A, the area, delta T, the change in temperature, and L represents the thickness. So how quickly energy can leave a building depends on what the building's made out of, the area of the wall, the thickness of the wall, and the temperature. If it's really, really cold outside, we're definitely going to lose energy faster. So it depends on those four things: what the wall's made out of, how big the wall is, how thick the wall is, and the temperature inside and outside. For instance, if it's 60 degrees outside and we have the thermometer set at 60 degrees inside, it doesn't matter how thick anything, whatever, no energy is going to flow. And then this equation right here, this last one, they're just rearranging. They're the exact same thing. They're just solving it for the letter K. So you multiply the L over, you take the A over, take the delta T, and then you end up with this equation over here on the right. So let's do an example problem with this one. It says calculate the energy transfer in a wall. And it's 2 meters by 1, so basically 6 feet by 3 feet. It's 4 centimeters thick, so it's probably like an inch thick, with a thermal conductivity of this, 0.1. Opposing sections of the wall are 5 degrees Celsius difference after 1 hour. So it wants to know the energy transfer, and that's the letter Q. So that energy transfer equation that we had before, it was Q equals P equals power, because that's the energy per second. Power equals K times A times delta T divided by the thickness. And they tell you the K, the conductivity constant, is 0.1 joules over seconds times meters times degrees Celsius. The area of our wall is 2 by 1, so that's 2 square meters. And then the change in temperature is 5 degrees Celsius. And then we're going to divide by the thickness, and the thickness is 0.04 meters. Now, again, units are really important. So meters, 1 meter's on the bottom, cancels off 1 at the top. This meters cancels off the other one. Celsius cancels off Celsius. And you're left with joules per second, because nothing else cancels. And a joule per second is a watt. So when I take 0.1 times 2 times, watch this, 5 times 2 is 10. 10 times this is just 1. 1 divided by 0.04 is 25. It's 25 joules per second, which is 25 watts. So this wall, I'm losing 25 joules of energy every second through this wall. The energy traveling through my wall, 25 joules every second. So every second, my heating system has to replace that. Okay, every second, oh, put another 25 in. Oh, put another 25 in. Oh, put another 25 in. How much energy is going through? Next problem. We're going to talk about what are called U values and R values. Maybe you've heard of R values before when you talk about insulation in heating for your house, residential, commercial. A U value, it's the measure of a material's ability to conduct heat. A U value, it's how much energy is traveling through it divided by the area divided by the change in temperature. So in the metric system, power is in watts, area is in meters squared, and change in temperature is usually degrees Celsius or degrees Kelvin. In the USA, power is BTU, British Thermal Units. Maybe you've heard of that before. There's a direct relationship between watts and BTUs. I could Google it real quick. How many watts are in a BTU?
3.41. According to Olympia Splendid, for W to BTU.
There's 3.41 watts for every 1 BTU. Area, square feet, delta T, change in temperature. Ooh, I think that power is BTU per hour. That's why this comes down here. BTUs per hour. R value. An R value, you'll see R values on insulation all the time. This has an R value of 5. This has an R value of 20, R30. Different types of materials have different R values. And it's the inverse of the U value. So if you've got a really big U value, then you have a very small R value. If you want to find an R value of a whole wall section, you add up all the pieces. That's what this means. Like here's an example. You've got a wall. You've got drywall on the inside of our wall generally. And they put fiberglass in between the wall cavities. Then you've got an exterior, they calling a foil-faced polyisocyanurate. It's a big word. Then there's a space, an air space, and then there's bricks. Because you want to have an air space, especially when you have bricks, because if it doesn't dry, it dies. Like when it rains, bricks are actually pretty porous. Excuse me. If you don't have an airspace back there for this to dry, this thing can rot, and then you're in all sorts of problems. So this question says, find the R value of the wall. Excuse me again. So there's two ways. You could be right here. This could be your R value. Heat could be leaving through here, or heat could be going through the frame. And we call this a thermal bridge. You'll see what I mean in a second when I do the math. So to figure out the R value for right here, you add up the R value. So you take 0.56 plus 19 plus 7.20. This is where I got the 19 from. Plus air actually is an insulating. This is how igloos work. They're mostly built out of air and snow, so they insulate pretty well. Plus the thickness of my bricks, which is 0.8. So I add up the total R value of this section right here, adding all those things together, is 27.73. Now, if heat was trying to escape here, adding up all those sections, again, add up 0.56 plus 6.88 instead of 19. So you can see the difference right now, 19 versus 7, plus 7.2 plus. You add these up, the total value here is going to be 15.61. And this is what's called a thermal bridge. In every wall, heat can travel through the different parts of the wall faster or slower. So if you were to look at a wall with a thermal camera, you can actually see where heat is leaving through the studs. You can see studs in a wall just by looking at them with a thermal camera when it gets cold outside. You don't need a stud finder. You can get a picture of where every piece of wood is, because this is called a thermal bridge. It's a bridge. Heat can travel across the bridge and go to the atmosphere through the wall. And this is why it's really important inside of, if you get into building trades, a 2x6 wall is better than a 2x4 wall, because you have, number one, you have less lumber, because you put a 2x6 wall, they call them studs, they're 2 feet apart from each other instead of 16 inches on a 2x4 wall. So number one, there's less wood. Number two, you have a more distance, a thicker space to put your insulation in. So it's better, but it's more expensive up front, as you'll find with all things that are efficient. They're more expensive up front, but then they pay for themselves over time. And then lastly, radiation. We talked about convection and conduction, and now how does heat travel through radiation? Like me, as a person, I don't know if you've ever laid in bed and you're like, oh, I'm really hot, and you stick your leg outside of the bed. You're giving off heat through your leg. You know, the covers are trapping that heat in, so you can get rid of your heat through what's called radiation. And this is called Stephan's law. It's, whoo boy, it's a lot of big words, man. The P stands for power. Again, it's joules per second. This is called the fudge factor. It's a constant, because normally all you have to do is you multiply the area, the temperatures, and then this emissivity, another fudge factor constant, and then you can get how many joules per second. So we put these constants in there to make area and temperature equal how much energy you're giving off per second. So in this equation, this is a Greek letter sigma. It's always going to be this number, 5.6696 times 10 to the negative 8th. Anytime you see this equation, that's what this number is right here. This will change depending upon the material. Like some materials will give off their energy faster than others. The A stands for area, and the T is temperature. Now remember, or look here, this is temperature to the 4th power. So here's an example problem where I would use this equation right here. It says, prior to dressing for school, a student is watching the morning weather to decide what clothes to wear. So they're assuming you're standing there naked. The bedroom is 65 degrees and your skin is 91.4 degrees. Determine the net energy transfer. So how much energy are you losing per second from your body for 15 minutes watching the weather? So if you're standing there for 15 minutes, how much energy do you lose through your skin? So let's figure out how much energy we're losing every second through our naked bodies, assuming our naked body has this surface area. So the bigger surface area you have, the actual faster you're going to lose it, I think. That's my hypothesis. I could be wrong. So here's the equation that we're going to use. It's that Greek letter, sigma, and then area, and that emissivity, and then the second temperature to the 4th power minus the first temperature to the 4th power. Oh boy. All right, so this thing, it was always that number. It was always the number 5.6696 times 10 to the negative 8th power. The area was 1.30. Now, I'm skipping over some of the units here just to save myself some space. But you gotta watch out when we get to the temperature because this is Fahrenheit. Oh, that's not good. The letter E for your skin was 0.9. And then the temperature. Remember that these are per Kelvin. So I wanted to make sure that when you go back here, that look here, this is Kelvin. Kelvin to the 4th power, Kelvin. So we want to make sure that our temperature is in Kelvin. Really important. You can't use Fahrenheit in this problem. You have to use Kelvin. So I just went on Google and I Googled what is 91.4 degrees in Kelvin, and it's 306. Google, what is 65 degrees Kelvin Fahrenheit in Kelvin? It's 291. Holy smokes. Multiply all of that stuff together and you get 105. It's 105 joules per second. Right? So you're losing 105 joules of energy through your skin every second. 105 every second. Ooh, so check it out. But you're doing it for 15 minutes. 105 joules every second. We're going to do it for 15 times 60 because that's how many minutes there. That's how many seconds there are. 15 times 60. So you take 105 and you multiply by 15 and you multiply by 60. And you get 94,500. Or 95 kilojoules. Holy smokes, what a lot of math. How much do you lose? We're losing 95 kilojoules in that 15 minutes. Well, kids, thanks for hanging in there. There's a lot of equations. You get that equation sheet to write that stuff down. Just always make sure, watch out for your units. It's really important that you're using kilograms, Celsius, Kelvin, seconds. Pay close attention to those units as you're going through.